In this video, we're going to evaluate limits using two different approaches. One approach will have us looking at graphs to evaluate limits, and the other will have us building numerical tables to determine limits. Let's look at example 1. Use the graph of the function f to evaluate each of the following. If a limit does not exist, write dne and explain why. Part A, f of -3. Part A is not a limit. They just want us to give the y value on this function at -3. And when we look here at -3, we notice that we have a point above it at 5 and a hole below it at -2. So the y value on the graph at -3 is going to be at 5. Part B, they want us to find the limit as x approaches 6 of f of x. So now we're going to think about x values approaching 6 from below and from above. And each of those x values, as we get closer and closer to 6, is going to have a corresponding point on the curve. So these points as we approach 6 from above, and these points as we approach 6 from below. Now the y values of these points are creeping up the graph this way and are approaching 6. So this limit is 6. Part C, the limit of f of x as x approaches -3 from the left. So now we're approaching -3 from below like this only. And as our x's are approaching -3, they have corresponding points climbing up the curve like this. And those points have y values that are approaching 5. Now in part D, we're going to find the limit of f of x as x approaches -3 from above. So now we're approaching -3 from this direction. And each of those x values that are just a little bit bigger than -3 are climbing up this part of the curve down here. And their y values are coming up this way towards -2. Even though we have a hole in the graph there, the limit still exists, and it is -2. Part E, the limit of f of x as x approaches -3. Now this is a two-sided limit. So we're approaching -3 from below, as we just saw, and we're approaching -3 from above, also, as we just saw. And what we notice when we look at approaching from above, we got -2. When we approach from below, we got 5. So the right-handed limit and the left-handed limit are not equal. When this happens, we say the limit does not exist. And the reason is that the limit of f of x as x approaches -3 from the left does not equal the limit as x approaches -3 from the right of f of x. Part F, f of 4. So if we look here at 4, we notice that the graph has a hole at 4, so our function is undefined there. Now we're going to look in part G at the two-sided limit of f of x as x approaches 4. In other words, we're approaching from this direction and that direction. And from below, we have points coming down the curve this way. From above, we have points coming down this way. And in both cases, it appears that the graph is approaching that hole, which happens to be at y equals 1. So this limit equals 1. So just because the function is not defined at a point, that does not mean the limit does not exist. H, find the limit of f of x as x approaches -2 from below. So we're approaching -2 from below, like that. And each of those x values have corresponding points coming down the curve like this. And their y values are going downward forever. So we can notate this two ways. We can say the limit is equal to -infinity, but -infinity is not a real number. So really, this limit does not exist due to unbounded behavior. Either answer here is acceptable. By writing negative infinity, we're describing the behavior of the function as x approaches -2 from below. In part I, we're going to do the same thing, but we're going to approach -2 from above. So we're now approaching in this direction, and each of those x values that are just a little bit bigger than -2 are going to have corresponding points like this, and those y values are shooting up towards positive infinity. So we'll write positive infinity here. Again, we could write does not exist due to unbounded behavior, but I'll leave it at that for now. Part J, find the limit as x approaches 0 from the right of f of x. So now we're approaching 0 from above, like this. When I say from above, I mean x's that are, in this case, bigger than 0. And each of those x's have points that are climbing up this curve and then back down a little bit. And those y values are coming downward towards 3. In part K, we're doing the same thing, but we're approaching 0 from below this time. So we're coming this way, and those points are creeping down the curve with y values approaching -2. Finally, in part L, we're looking at the two-sided limit of f of x as x approaches 0. So we're basically looking at the previous two limits, like that. And we notice that the limit as we approach 0 from below does not equal the limit as we approach 0 from above. So that means that the two-sided limit does not exist. Given this piecewise defined function f of x, we're going to graph the function, we're going to find a few limits, and then we're going to find the x values where the limit does not exist. With piecewise defined functions, it's often best to start with the restrictions on the domains of each individual function. In other words, we're going to focus over here at these bounds for our x values. And so what we notice is in purple, we're going to do something for all x's that are less than -2. And so that's in this direction on the x-axis. And then in green, we're going to look at this portion of the x-axis from -2, including -2, all the way up to 1. And then in blue, we're going to be looking at all the x's that are bigger than 1. The easiest way to graph these is using transformations. And as just a quick review of what I'm talking about here, if we look at the function in purple, meaning y equals -x plus 3 squared plus 4, that's essentially a quadratic function because we've got an x squared as our highest degree term. And so remembering a few things about transformations, if I have the function y equals x squared, that's often called the parent function, that looks something like this. And if we now just look at y equals x plus 3 squared, that's the exact same function, except it's been shifted 3 units to the left. If we continue and put a negative in front of that, like this, we get the same function again, shifted 3 units to the left, but now it's been reflected about the x-axis and looks something like that. The last step is to add 4 to the back. And what that's going to do is it's going to move every single point on this curve up 4 units. So this last one is the graph that we want. But remember, we have a restriction on the domain of this graph. We're only going to graph this parabola for x is less than -2. So we've got our -3, 4 right there. And then at -2, we could actually plug in our -2 here and quickly see that we have a -2 plus 3 squared like that, which will give us a 1 squared plus 4, which is going to equal 3. And notice that we have a strict inequality here in purple, so our x cannot equal -2 on the purple graph, so we're going to put an empty circle there. So this portion of the graph is going to look something like that. Let's continue on with green. So back to our transformations, y equals absolute x is the most basic absolute value function and looks something like this. Y equals absolute x plus 1 is going to shift this graph 1 unit to the left. Again, we only want to graph this green absolute value function between -2 and 1. We could plug in -2 in here, we could plug in 1. I think when we plug in -2, we get a positive 1 because we have absolute value of -1, and that's going to give us this point here. And then we have our vertex right there. And then we plug in 1, we get a positive 2. And again, we have a strict inequality, so we'll put an open circle there. Finally, in blue, we're being asked to graph the ln function. Hopefully you remember what that looks like. The ln function has a vertical asymptote at 0. It goes through the point 1, 0, and has a graph that looks like this. And we're being asked to graph this for x is bigger than 1. So we're going to go ahead and put an open circle here, and we're getting something like that. So this is the graph of our piecewise defined function. In part B, they want us to find each of these limits. In the first one, we have the limit of f of x as x approaches -2 from below. So we're approaching -2 from this direction. So that means we're on the purple graph, and we have points on the purple graph falling down this way towards a y value of 3. Next, we're going to approach -2 from above, like that. And we have points on the graph coming up the green portion of the graph, and those y values seem to be approaching 1. Now we're looking at the limit of f of x as x approaches 1 from below. That means we're coming this way. Again, we're going to be on the green graph, and the points climbing up that green graph have y values approaching 2. And finally, we're going to approach 1 from above, which means we're approaching this way, and the points on that blue part of the graph are coming down towards y value of 0. So we just answered each of those limit problems graphically using the graph we generated. Now, for part C, they want us to find the values a where the limit doesn't exist. Well, that's happening here because the right-hand limit and left-hand limit are not equal, right there. And it's also happening here because the right-hand limits and left-hand limits are not equal. So we're going to say a equals -2 and a equals 1. Let's look at the next example. Example 3, evaluate g of x equals 1 minus cosine x over x squared at the given values of x, correct to 6 decimal places. So here we're doing a numerical method where we're going to fill in the table and evaluate the limit as x approaches 0 from the right of this function g of x by plugging in successive values of x getting closer and closer to 0 from above and seeing what the y values are approaching. So using a calculator, we're going to have 1 minus the cosine of 1 over 1 squared. And because we have no degree symbols here, we're going to assume we're in radians, so make sure your calculator is in radians. And then we'll repeat this process with 0.5, 0.25, 0.1, and so on. Now we'll transfer each of these values into our table. Finally, we notice that as our x values approach 0 from above, our y values appear to be approaching 0.5 or a half. Example 4, determine each infinite limit. In part A, we're finding limit of 5 over x minus 4 as x approaches 4 from below. So we could graph this and observe the behavior of the function as we approach 4 from below, or we could build a table. So let's plug in values for x that are just a little bit less than 4. For example, 3.9, 3.99, 3.999. And then we'll plug them into the function to see what's going on. So first off, notice that when we plug in 3.9 in for x in the denominator there, we're going to get a negative 0.1 like that. And so we end up with 5 over negative 1/10. And if we plug in 3.99, we're going to get negative 1/100th. And then you can easily see that when we plug in 3.999, we're going to get negative 1 over 1,000 down there. Now, dividing by a fraction is the same as multiplying by its reciprocal, so this is negative 50. And this one is negative 500. This one's negative 5,000. If we continue like this with values even closer to 4, but still less than 4, we're just going to keep getting negative results that are getting further away from 0. So this limit equals negative infinity. We could have also looked at part A graphically. If we think about the function 1 over x, it looks like this, with a vertical asymptote here. Subtracting 4 from x is going to shift this function 4 units to the right, putting our vertical asymptote at x equals 4. And finally, multiplying by 5 will simply stretch this graph vertically by a factor of 5. And so you can see that as we approach 4 from below, our y values of these points are going towards negative infinity. In part B, we want to find the limit as x approaches negative 2 from above of x minus 2 over the quantity x plus 2 to the third. So again, we can think about plugging in values of x that are just a little bit bigger than negative 2. For example, negative 1.9, negative 1.99, negative 1.999. Now, when we plug these values into the numerator, we're getting numbers that are very close to negative 3. So let's just think close to negative 3 in the numerator. And in the denominator, when we plug in negative 1.9 and add 2 raised to the third like that, this denominator is going to give us positive 1/10 to the third. So basically, we've got negative 3 on top, or very close to it, and we have 1 over 1,000 in the denominator. When we multiply by the reciprocal, we're going to get negative 3,000 there. So this is approximately negative 3,000. When we change this value to negative 1.99, we're going to get 1 over 100 here to the third power, which will give us this. Multiplying by the reciprocal, here we're going to get negative 3 million. And you can quickly see that the function is approaching negative infinity as x approaches negative 2 from above. With part C, we want to find the limit of cosecant x as x approaches pi from the left. So first of all, let's remember that cosecant x is equal to 1 over sine x. And if we think about the graph of sine x, it looks something like this. And from the graph of sine x, we can generate the graph of cosecant, basically taking the reciprocals of every y value. When sine is 0, cosecant is undefined and we have vertical asymptotes. When sine is 1, cosecant is 1. When sine is negative 1, cosecant is negative 1. And we end up with a graph that looks something like this. Now, if our x's are approaching pi from below, our x's are approaching in that direction towards pi, we end up with points climbing up the cosecant graph like this. And so we have that this limit is equal to positive infinity using a graphical method. Now go ahead and do problems 1 through 8.